In this video, we will explore the concept of work in physics. We will define the work done by a force and be able to calculate values for work done by a constant force. We will then see how work done by a force is equivalent to a transfer of energy. Afterwards, we will gain an understanding of power as the time rate of doing work, and we will cover efficiency in energy transfers. In everyday language, we think of work as any activity that requires physical or mental effort, such as repairing a bicycle or writing a report. But in physics, work has a much more precise definition. In these two examples, work is done by exerting a force on a body while that body moves from one position to another, or in other words, undergoes a displacement. And this is what the physicist's definition of work is based on. In a generalized case, let's consider a body that undergoes a displacement of magnitude s along a straight line, due to a constant force F that makes an angle θ with the displacement. The work done by this force, denoted by capital W, is then defined as the product of the displacement s and the component of the force acting in the direction of the displacement, F cosine θ. The SI unit of work is the joule, where 1 joule is defined to be the work done when a force of 1 Newton moves a body by a distance of 1 meter in the direction of the force. From this definition, if force and displacement act in exactly the same direction, such as in these two examples, θ will be equal to 0 degrees. So cosine θ will be equal to 1, and the equation for work done reduces down to the following. For example, if a force of 3 newtons pushes a box for 2 meters, the work done will be 6 joules. Moreover, if force and displacement are at an angle to one another, the perpendicular component of the force, F sine θ, does no work on the body. If we plot a force displacement graph for a constant force, this will be represented by a horizontal line as the force does not change. Now notice how the area under this graph is a rectangle, with a base of length s and a height of length f. The area of a rectangle is base times height, giving f times s, but this is our formula for the work done by a constant force, provided force and displacement act in the same direction. Therefore, the area under a force displacement graph can be used to calculate the work done by a force. The advantage of a force displacement graph is that the area under the graph will give the work done by a varying force. Consider this force that is increasing with displacement. We can split the graph into a triangular section and a rectangular section and calculate each area separately. The area of a triangle is given by half base times height, with base length 10 meters and height 3 newtons, giving 15 joules of work done. Similarly, the area of the rectangle with length 10 meters and height 2 newtons gives 20 joules of work done. The sum of both areas will then give a total work done of 35 joules by this varying force. It is important to understand that work done can be 0 and also negative. Suppose that a person is holding a heavy object motionless for some amount of time. In our everyday definition, we may think that it is hard work to hold a heavy object for an extended period of time. But in fact, 0 work is done on the object because there is no displacement. Now imagine that a person is walking with a constant speed while holding a heavy object. The heavy object will have a horizontal displacement, but the upwards force exerted on the object has no component in the direction of the horizontal displacement. So θ would be 90 degrees in this case, and cosine 90 degrees is 0, hence 0 work is done even in this scenario. Now let's consider a ball on a string that moves in uniform circular motion. Recall that in circular motion, there is a force that is always directed radially inward known as a centripetal force, and in this particular example, the centripetal force is provided by the tension in the string. However, the velocity of the ball at each point along its path is always tangential to the circular path, which means that the instantaneous displacement of the ball will also be tangential to the circular path. Therefore, the angle between the tension force and the displacement will always be a right angle. As cosine 90 degrees is 0, this means that the work done by a centrifugal force on an object moving in uniform circular motion will be 0. When the force has a component opposite to the displacement, cosine theta will be negative and the work done will be negative. For example, when an object is lifted, an upwards force is exerted on the object and the object's displacement is upward, so the work done by the lifting force on the object will be positive. If we now consider the gravitational force, this acts downwards on the object. The downward gravitational force is opposite to the upward displacement, so theta will be 180 degrees, and the work done by the gravitational force on the object will be negative. Because of this, we always ensure that we specify what force is doing the work. We will now link the idea of work done to energy. A way to think about the concept of energy is that energy is needed to make things happen. For example, in order for someone to push a box, the person must have a store of energy, which is usually chemical energy from food. The person will use their energy to cause the box to move. The person will be exerting a force on the box, and since the box moves from one place to another, the person must be doing work on the box. This is why energy is often described as the capacity to do work. Now, any object with motion will have kinetic energy, so the box must have gained kinetic energy from the person's chemical energy, and this process is known as a transfer of energy. If we consider friction acting on the box, this will oppose the box's motion and cause the box to slow down. Friction does negative work on the box, and this causes a transfer of energy from kinetic energy to thermal energy. In both of these examples, work is done by a force on an object, and it results in an energy transfer. This is how these two quantities are linked together. Work done is another way of saying that energy is transferred. There are many different types of energy, such as kinetic energy and potential energy, and many different possibilities of energy transfers, but these will be explored in detail in another video. When energy is transferred, we might concern ourselves with how much time it takes for this transfer to happen. The quantity used to describe this is called power, and in physics, power is a measure of the rate at which energy is transferred. Since energy transferred is equivalent to work done, mathematically, power, denoted by capital P, is equal to the work done divided by the time taken. The SI unit of power is the watt, where 1 watt is defined as a transfer of 1 joule of energy in 1 second. Moreover, if a constant force F moves a body in the same direction as the force, recall that the equation for work done is reduced to force multiplied by displacement. This can be substituted into the equation for power as follows, and then we can recall that a displacement divided by a time is equivalent to a velocity. Therefore, power can also be calculated as the product of the force applied to the body in its direction of motion and the velocity of the body. For example, if a force of 5 newtons is used to push a box at a speed of 2 meters per second, the power will be 10 watts. This means that 10 joules of work is being done every second. Sometimes when work is done on an object, energy can be lost or dissipated from the system because it is transferred into less useful types of energy, such as thermal energy. The term efficiency is used to quantify the amount of energy that is transferred to useful output energy. Efficiency, denoted by eta, can be calculated as the ratio of the useful energy output to the total energy input. Efficiency has no units and is often expressed as a percentage. As energy divided by time is equivalent to power, efficiency can also be defined as the ratio of the useful power output to the total power input. Referring to our earlier example, if only 7 watts of power actually moves the box, then the efficiency would be equal to 70%. We will now provide a final summary of the key understandings from this video. Work is done when a force acts on a body and causes the body to undergo a displacement. The work done by a force is calculated as the product of the displacement S and the component of the force acting in the direction of the displacement, F cosine theta. As a result, work done can be positive, negative, or even zero, depending on the angle between the force applied and the displacement. The area under a force displacement graph can be used to calculate the work done by a force. We also saw that the work done by a force is equivalent to a transfer of energy. After this, we introduced two more quantities: power as the rate of energy transfer or the rate of work done, and then efficiency as the ratio of the useful energy output to the total energy input. This now concludes our video on work done and energy. Thank you for watching.